Hi everyone, I welcome you all in the next lecture of quantum mechanics. So in previous lecture, we have seen the derivation of Schrodinger's equation from the classical system. So in today's lecture, we will see the Born statistical interpretation. So let me share my screen and then you will understand. So I hope my screen is visible to all of you. And just 1 second. Yeah, to make it a bit small so that it will be easy for me to explain. Yeah, great. So here, when we talk about Schrodinger equation, it's one of the most fundamental equation in quantum mechanics. However, there is very important, question associated with it. So when we solve the Schrodinger equation, so the solution that we obtain in the wave function represented by uh, psi of xt, so the problem is that this wave function is generally a complex function because the Schrodinger equation, itself contains an imaginary number I that is equals to root of -1. So naturally, a question arises: what exactly is this wave function, and what physical quantity does it represent? That is what in this lecture we are going to understand thoroughly, and we'll see what is the physical significance of calculating this wave function from the Schrodinger wave equation, right? So this particular interpretation has been given by Born. That's why we call it as Born statistical interpretation. And here you can see that Max Born proposed that the wave function itself does not represent any, directly measurable quantity. Instead, its modulus square gives the probability density of finding the particle at a position x and time t. So here you can see that how can we calculate the probability density? That is equals to modulus of psi xt square, that is the wave function at any particular location and time square, that is equals to the complex conjugate of wave function that will be multiplied with the wave function at that particular instant and time. So this is the probability density of finding the particle at position x and time t. So here you can see that the probability density in an interval can be defined as, the probability of A, which less than x is less than b at any particular time t, that is equals to integral over a to b psi of xt squared dx. So this probability of, this gives you the probability of locating the particle between the position x and x equals to a and x equals to b. So on y-axis, basically what happens, you plot, the probability density, that is modulus of psi xt square, and on x-axis, that is the position of the particle. And if you see the area under the curve, that basically gives you the probability of finding the particle between point A and B. Right, so that is one of the features of the quantum mechanics, but we need to understand with respect to the classical physics as well. So when we talk about the classical physics, so there is a always a clear physical quantity associated with them. For example, in wave, we see wave on a string. The wave represents the displacement from the mean equilibrium position, right? That you can see here. In sound wave, basically, that basically corresponds to the pressure variation traveling, through the medium. In electromagnetic wave, the wave represents the oscillating electric and magnetic field along the perpendicular direction. So all these quantities are physically measurable, and that however, in quantum mechanics, the wave function does not directly correspond to any measurable physical quantity. So the wave function itself is not something physical in classical sense. Instead, it is a mathematical function that contains informations about the quantum system. So this led us to a major conceptual difference between the classical mechanics and the quantum mechanics as well. So in classical mechanics, basically we study the Newton's law of motion, that is equals to F equals to ma, and if force is known, then we can calculate the position, and based on that position we can calculate the exact trajectories of the particle at different location and different time. And basically, what we can calculate precisely in classical mechanics, that is, the velocity of the particle, that is v dx by dt, momentum, kinetic energy, and another features as well. So if we talk about the nature of the classical, physics, that is deterministic in nature, and if all the initial condition and force are known, then the future of the particle can, in principle, be predicted exactly. So then, coming to the quantum mechanics, however, that works very differently. So we in quantum mechanics, basically we solve the Schrodinger equation that you can see here on the screen, and we do not directly obtain the exact position or trajectories of the particle. Instead, we obtain the mathematical wave function psi that I have already discussed about that, and the wave function only gives the probabilistic informations about where the particle may be found. So that here you can see that what we can obtain in the quantum mechanics, that already I have described in the previous slide, where we can calculate the probability of finding electron between the point A and point B using the probability density. And then what is the nature of this system basically? So in quantum mechanics, we see this is a very probabilistic in nature. We do not get the exact position or trajectories of the particle. We only get the probability of finding the particle in a different region. And in quantum mechanics, basically for one set condition, we get many possible outcome. So this is all about the quantum mechanics, but the key breakthrough in understanding this was provided by Max Born in 1926 through what is now known as the Max Born statistical interpretation. So this quantum mechanical system that does not tell us exactly where the particle is located. Instead, it tells us the probability of finding the particle in different region of a space. And this probabilistic nature is one of the deepest and most surprising, aspects of the quantum mechanics. So basically, what happens? This interpretation introduces a major philosophical, shift in the physics. So classical mechanics is deterministic in nature, and quantum mechanics is fundamentally probabilistic. So even if we know anything possible about a quantum mechanical system, quantum mechanics can only predict probability that that does not predict the exact outcome. So this probabilistic interpretation, disturbed many scientists, that including Albert Einstein as well, and who famously said that God does not play dice. What do you mean by these things? So Einstein was, uncomfortable with the idea of the nature at its most fundamental level might be probabilistic rather than deterministic in nature. However, the quantum mechanics repeatedly agreed with the experiments, and the probabilistic interpretation become accepted as a core principle of the theory. Interestingly, what happened? Max Born probabilistic interpretation was, inspired by Einstein himself while explaining the photoelectric effect of light. Einstein connected the wave and particle nature of the light. In classical electromagnetism, the intensity of light is proportional to the square of the wave amplitude. So Einstein related this intensity of the particle or intensity of number of uh, photons present in the beam. So, inspired by this idea, Max Born proposed that the square of the quantum mechanical wave function should similarly represent the probability density of the finding of the particle, such as electrons. So, therefore, the wave function in quantum mechanics is not directly measurable physical quantity like displacement or electric field. Instead, it is a mathematical object that contains all the information about the quantum mechanical system. By taking a modulus a square, we obtain the probability density associated with the particle's position and other measurable quantity as well. So this interpretation forms the foundation of modern quantum mechanical system, and that completely changed the way we understand the physical world at a microscopic level. So in summary, we can say that The classical mechanics is deterministic in nature, and we can exactly calculate the trajectories of the particle that basically predicts exactly what will happen. On the other hand, quantum mechanics basically it is a probabilistic in nature that does not exactly gives the trajectories of the particle, but that can predict, the probabilities of outcome. So before concluding this talk, I'll tell you that the Max Born was the scientist who proposed this, theory in 1926, and that showed the quantity that is modulus of psi xt square, that is a wave function square, that will be equals to the complex conjugate of psi xt star and psi xt, that represents the probability density of finding a particle at a given position. And this is all about the Max Born interpretation. That is one of the most important theories in quantum mechanics. Okay, so thank you all for attending this lecture. In next lecture, I'll be talking about the normalization of wave function, and then I'll move towards the particle in a box in 1D and 2D. Thank you all. See you in the next lecture.